he can see the solution and then he can select any of the solution he is interested in. That also it will be given with the priority, like which is correct, which is the highest priority. So all those things can be formulated and then provided to the operator. So now it is up to the operator to choose the best solution. Here also automation is possible in terms like the system can choose what is the best solution by itself. So these are the basic principles on conflict management. Now there is a question like when I see a conflict for a train, I give a solution. But if I apply the solution, you don't know there will be implication on the another train. So the impact will go on. You will impact across all the trains across the network. So you need to handle this kind of solution in a more optimized way. So when you give the solution, you have to consider all the train in mind and give the solution. So that is what we call it as a optimization. So till now you see these are all common functionality across all the TMS. For any TMS to say I am a full-fledged TMS, these are the functionality should be there as part of the system, so that you can manage the complete network of mainline system, and then you interface with all the specific external system, whatever is required, which will impact your planning, even the crew management. Like as per the plan, you know, okay, there is a particular crew supposed to get in the train to act like a pilot. Okay? But due to some changes in the crew system, the crew is on leave today. That information also has to be populated to the TMS. Then only you can adjust the plan and reroute the train on the worst case. Otherwise, you have to reallocate with a different crew. So some changes has to happen inside the TMS based on the external world. Everything has to be interfaced. So if you see on the TMS front, there are two critical parts. One is to interface with the interlocking. Another is to interface with other external systems. Specifically for interacting for each line, you may have a different TMS. So that's a major part on external interface. Like sometimes we deal with the like a standard for Unix standard, like UIC 407 leaflet, that is meant for TMS to TMS interfaces. Okay, so sometimes we have to deal with that. Like some customer comes and say, okay, I need to be compliant with the UIC. So we go with the standard. Sometimes we go with a customized version of UIC. That's most of the case. This is the solution. Like they will use the basic interface requirement of UIC, but on top of that they customize according to their need. So we have some reference with respect to both the case. So we have customized UIC implementation for interfacing with the adjacent system. So adjacent TMS is a key element in interfacing with external system for mainline. So these are the basic and relevant functionality for TMS. But as an interface point, the key is interface to interlocking and interface to external system. Other two major areas that need to be considered. Okay, and now now based on direction and solution, so it becomes a director. So it's a controller, it's a planner, it's integrator, and it's director. Now the systems are coming up with regions to country level. Like that's what we call it as a national level system. For example, Sweden, it is totally 15,000 kilometer line will be managed by a TMS, Centralized Control Center, for a 15,000 kilometer line. So that means it's a national system. For Denmark, half of the country is the east part is managed by Alstom and the west part is managed by Thales. So on France, the whole system planning will be managed by Alstom. So the systems are moving towards national system. It's no more a section or a line or a region. So it can be applicable, but the future is to move TMS for a complete country. Okay, so when it goes to country level, then the complexity increase. The number of people works at a time on the system. Like it will be like 600 workstations, 600 people will be managing the DMS. That means you need to have a provision to communicate and negotiation between the user's choice, like a decision making. One user, whatever the decision he makes, it will impact the other people area. So you need to have a negotiation and you need to have a collaboration. And then you need to have a better workflow management. So whatever I'm saying, it is very specific for the advanced system, but like national level system or at least like state level system. So these features are very highly advanced, but these are all part of TMS. So when we say coordinator, so these are things has to be considered. So in a way, if we look at the TMS, it's a controller, and then it helps in planning, and it also integrate with the external integrator, and then it's a director which talks about decision making in terms of conflict, and also it's a coordinator. So you can combine all this as a matter of traffic management system or a train management system. So this should be part of any TMS. Okay, so this is just a brief about the philosophy, how we arrive to a full-fledged TMS from starting. So now you can see each and every aspect has a meaning and a need. So that's how it arrived. So in simple word, if you put it, you can see the bottom, it's interlocking and RBC or TMS specific signaling system. You need to have a field interface. Okay, and you need to have a monitor and control, which is a basic functionality. And then you talk about planning and optimization. For any system, you need to have a diagnostic. So our interest is on this path. Say you need to have a dedicated environment or gateways to talk about field interface. So that these can be generic. So you can consider these are the core TMS functionality, and this is only the interface to the field. So by this we can talk like how it is possible to manage. Say, so, and of course this outside layer, you can see there is a HMI to deal with the operator interfaces, and then as I said there is a specific external interfaces that will deal with all the possible external interfaces. Okay, so this is a very specific flow. Like it's not that you need to have a complete monitor and control as a SIL2, but there are certain functionality in TMS control level can be SIL2, like a TSR can be SIL2, or blocking way restriction or possession. Setting the possession may not be SIL2, but revoking the possession or way restriction could be SIL2. So like that. So if you look at this point, like starting from field, monitor and control and HMI, you can consider the field interface like a field gateway play a major role. So this is where we talk like it is about abstracting or hiding all the different kind of interlocking into a unified way. When it gives to TMS, it's a unified approach. Okay, so all the different kind of interlockings, they may have a different kind of like a way of communication or a different way of populating the information, and everything will be hidden here. But we deal only this part as a TMS core functionality, so that the adaptation to the different field can be managed effectively. So that's why we keep it as a separate. So generally we call it as a field gateway. There you can have any type of interlocking or any type of interface to the PLC or RTU. So you can manage whatever you want. This is very specific. For every interlocking, we may have a specific module inside, and then this is connected. So finally, it goes to monitor and control. That is using the standard interface. So we don't feel anything inside the TMS. Once you design the TMS, you don't need to already decided, and then the field gateway will talk in the same language to the monitor and control. That means you can only focus on this part to the new interlocking or existing interlocking. So your focus will be only on this part, and it is nothing to do with the TMS functionality. So that's how we generally decide on field gateway. So this is about overview. Now I'll request Mahesh to deliberate on adaptation of different field gateways with respect to TMS, how we interface.
Thanks, Ravindran.
Yeah. Yes.
Yeah. So when it comes to integrating the different interlockings into the TMS or CTC system, we look at the key points, which are the key points to consider in solution design. So we can have different things with different layers. So there are some systems, old systems, which have legacy interfaces like RS232, RS422, like that. So in such cases, we define specific gateways to do the data interface in a specific format, and then make it into the unified system of TMS. Okay. Similarly, at the application level, even if the interlocking has the TCP kind of support, still it may have a different application protocol for the communication. So in such case also, we define a specific gateways or adapting the gateways to communicate with the interlockings from the TMS, centralized location. So in such design, some of the key points to consider is the system response time, because we are adding additional layers of communication or conversion of protocol or unification of the interfaces. So there will be some additional time required for the communication, maybe. So in case of, for example, when the system is operated in a relay control, when the operation is done locally and a relay control interlocking, when we migrate it to a centralized control through the conversion of signals using PLC or RTU, so here it is to acquire the signals, the relay signals, the inputs and outputs, the digital inputs and outputs are to be fed into a PLC or RTU to acquire them onto a network, and then this data is transferred over a network to the centralized location through a backbone network. So in such case, there will be some additional time required for acquiring the data and processing the data at various levels, and then also to process the final control and implementation of the control logics at the central level, and then giving the feed back to the feed for the controls. So all this total time that is required for all this processing will have to be considered. So that's one of the key design factor in such a gateway design. There are some cases where the field conditions will be required special attention, because the installation are very old, so we may have to do some rewiring to link it to the new system, or to connect it to, for example, relay interlocking. You may have to tap the input outputs to connect to the RTU or PLC, or you may have to rearrange some of the wirings or something for adapting it to the TMS. So in such cases also we have to be carefully understand the need, and then how to implement the system without impacting the current system and also the operations. So that is one of the key factors that we consider in the implementation of TMS or CTC in an existing system. There are other cases where the issue of not having the complete information, or the drawings or data or the design documents of the existing may not be present. So we may have installed something, and over the years there might have been some changes to meet some challenges that the people would have implemented some changes which have not been documented properly. So that is another challenge that we'll have to consider during the design or the implementation of TMS. So these are the key challenges. So based on these challenges, we will now show the different scenarios which we can consider for integrating an existing system or a new system together into the TMS system. Next slide, please. interface overview. So TMS has three parts. One is the operational interface, that is the HMI and all the operators who will use the system. Then the external systems with different kind of external interfaces will be there, and another interface is the signaling system. So in this signaling system, it could be interlocking gear TMS or specific field devices with which the TMS has to integrate. So these are the three key interfaces that we consider for interfaces. So in the interlocking interface, we will show in the next slides. So different types of interlocking, as I mentioned, it can be integrated into a single TMS. So you have legacy systems, relay interlockings, electronic interlockings with the legacy protocols, and the transport layer implemented with modern interlocking with the TCP communication. So different types of interlocking can be integrated into one TMS system, and then TMS HMI for operational people with to the control and monitoring of the system for the railways, and also to understand the performance, to do some performance analysis, everything we use the operational interface. We have the external interfaces to communicate with non-signaling systems for many functional and operational needs. Okay. So this is the overview of the interfaces. So now we will move on to the field interfaces part. Okay, so this is the topology on which we implement the TMS interface to the field devices. So normally the TMS is a server client kind of system with centralized or distributed servers processing the data. So this is mainly a data processing, so capturing the data from various part of the system, processing it and making some decisions, and then sending out controls based on those decisions. So it's mainly on a server-based system. So it will be centralized or with the sectorized approach. So you have multiple servers which work on a communication network. So the first thing we do in bringing the field data to this server interface is to get the data onto a network. So if there are relay interlockings which have the digital signals, the relay contact status, that we have to first acquire and feed it to a network data. So we will have some kind of PLC or an RTU or a field interface unit, sometimes we call it as, which can take these digital IOs and then send the information of those IOs on a network backbone, okay, protocol. So this is the first stage. So you may have a redundant approach where you have for a simple approach, you may have one interface, or in the case of redundant approach, you may have redundant path to ensure that you don't have any data loss and your processing is redundant in case of losing one channel or so your operation is not hampered. So that's why we can have redundant or singular interface to the existing relay interlocking. So the first point is, in case of relay interlocking, we have to bring the data onto a backbone network on a network transmission. So first thing is to capture the digital IOs into a PLC or RTU, through the PLC or RTU to the network. This first approach we do. Okay, so this PLCs, there are different types of PLCs considered for such. Second one is an interlocking which can already communicate on a network. So we have systems which have a serial or communication links which may not be a TCP link or a specific link. As I mentioned, some of the old SSI interlockings, you may have an RS-232 link on which you can communicate the information of the field and controls that you have to send to the field, or you may have a TCP link also. So there are different types of serial communication that interlockings come with. So this also we integrate into the TMS using gateways, because there are different types of communication transport layers which will have to be unified when it is managed by the TMS, or because the protocol that is supported by the interlocking is a specific one. So in that case, we have to have field gateways which convert the protocols into a common protocol that the TMS or CTC can handle. So these gateways are sometimes designed with the requirement of safety, because you have many controls that you send to the field for blocking condition blocking, speed restriction kind of thing. So we have sometimes the safety layer implementation. Then there can be different types of protocol merged into single gateways. So that is also another option that we design based on the requirement. Okay, so this is the second types of interface that we do on field gateways. Next one. So then when we say, as I said, we do a centralized system, as Ravindran mentioned. Now the systems are going for a national level implementation. So we have 1 or 2 TMS controlling 10,000 of kilometers of line. So in those part of the line, there will be different types of signaling controls implemented. It will not be one type, but many types of interlockings because of the various implementations. So this gateways now will communicate with those specific interfaces and merge all of them into a unified system called Centralized TMS. So you will have the implementation of the interlocking and also the trackside detectors. So there are some cases where you have, apart from the interlocking, there are some trackside field equipments like hot axle detector. In some countries, you have the point machine heating the system because of the snow issue. You have to heat the point machine before the operation can start. So such field devices are also there. So such field devices, in some cases, we are directly acquiring them through gateways, or sometimes they can be communicated through the interlocking. So both options we implement, so based on the requirement. Sometimes it can be the field devices are also acquired through the PLCs. Basic is the field data, which are in discrete data or digital IOs, will have to be first brought onto a unified communication platform before it is being processed by the interlocking or by the CTC or TMS system. So these are the different types of gateways that we are showing here. So in some case, for example, your CTC or TMS has a communication protocol, a unique communication protocol. So you have the different gateways for managing the different types of interlocking to communicate with the different types of field devices. So all those gateways we implement and then bring it onto the common platform, the common protocol, on which it can communicate with the centralized control system. Similarly, for in an ARTMS implementation, we also have RBC gateways when centralized TMS has to send the information to the RBC and also to collect information from trains. Okay. So this is how the architecture can build. The functionalities of TMS, the 4 functions which Ravindran mentioned during the initial presentation about planning, decision support, and all those interfaces, external interfaces, all those core functions are implemented on one set of functional servers. Then you can have one set of gateways aggregated onto a single implementation, and these gateways will communicate with interface with multiple types of interlockings. So the central communication, central core function will send make the decision, send the commands through the field gateways to the specific interlockings. Then all this data will be flowing in a network, common network, which are shared by the gateways and the centralized system. So all of them will share a common network, and this network will carry the data to a particular sector or section, and those sections will get the data on the specific interface protocols that they support to make to implement the final field control. The final field control of signal aspect control, point control are implemented by the interlocking finally. TMS is only giving the first level of control, but the final output to the field is generated by the interlocking. So the data has to pass through the interlocking, the safety layer of the interlocking. Okay. So the other different architecture of field gateway is you have the gateways per section. As I mentioned, you have multiple sections to be integrated into a centralized TMS or CTC. So we have different types of gateways. So you know a particular section is having one type of field devices and interlockings. So you have one gateway for that, and in another sector you have all specific one type of interlockings and gateways. So single gateway can manage those particular type of interfaces, and the second gateway can manage the second type of interfaces. So we sectorize based on that and implement those gateways for a particular section, and then integrate into the backbone. Then again carrying the data to the centralized control, where the processing of these data is done, and then all the decisions are taken, and also based on the control done with the decision made by the system. So the
Mahesh,
requested the operator.
Mahesh,
The 5 controls are sent to specific gateway, and through this gateway
Mahesh, you're able to hear me?
Yes.
Yeah.
Yes, sir.
Slowly, I mean, some lag is there. You can just
Yes.
roll back and then. So, fine. Carry on.
Okay. Okay. So this slide, I think, is it clear, or should I go through it again? So this is an implementation where, yeah. Okay. So where we have gateways implemented per section. Well, I was mentioning in a particular section, when we have a similar kind of field devices and interlocking, we define one gateway for that particular section. So similarly, you have multiple sections implemented for interface on specific gateways, and then those sections are integrated into the centralized TMS or CTC. So that is how the second type of architecture for field gateway interface. Okay, so next. Ravindran? Okay. So as we were seeing, since the CTC is now taking over the full operational control of the railway, you need to have redundancy built into your equipment level, your application level, and also the network level. So these gateways are implemented with redundancy. So you have the master and standby systems running at all the time, and any failure, in case of the master failure, the redundant system will take over. So we have two gateways interfacing with a particular sector, and then the master and slave configuration, master and standby configuration, and both of them also can communicate with the centralized system, but the final control and the commands which go to the field will be handled by only one system at a time. So there is no overlapping controls sent towards the field. So at the internal level, both of them will be processing the data, they will be getting the data and synchronize the data between them, but the final control will not be sent by both. So one of the system will act as a master, and the other one will act as a standby system. Okay. So this is an example of such gateway implementation that we refer to. So you have different types of field interlockings. You can see on the left side there was an implementation of Siemens systems, and on one side of the line there was implementation of Bombardier side. So we implement different types of gateways, connecting them onto a IP network. Then you have some specific part of the line which has to be similar to a relay interlocking, so we have to connect to an RTU. So you can see with an RTU, signals, the discrete IO signals are captured to an RTU. To an RTU, they are communicated on a backbone network, and then on different protocols, these data are acquired, and then all these data are combined into the field gateway at the TMS level, where the final unified data approach is done, and this data is fed to the TMS system for its processing. So it can interface with multiple sectors at the same time with the network. Because of the network approach, multiple sectors can be simultaneously sending the data to the TMS, and also the TMS is sending the controls to the multiple sectors on the backbone network, and then these data are fed to different types of RTUs and converters to feed it into the interlocking and also to the field controllers. So this is how the field gateway implementation. So as I mentioned, different types of approach to harmonize the interlocking types. So you can have data concentrators. So one is to collect the data and aggregate them and feed it into the gateways. Okay, or we can directly communicate without the data concentrators. So in some cases, the data has to be aggregated, and in some cases the TMS has only the gateway. So data concentrator is mainly when you have one type of system, instead of having the gateway for the multiple systems, we aggregate them, concentrate into one unit where the data is concentrated. So this concentrator gets the aggregate of multiple interlockings or field devices, and then the gateway will do the conversion of the unification of this data transfer, and this unified data is fed to the TMS. And in second case, where you have the interlocking itself, especially when it is a communication supported interlocking like TCP based communication, then we have the field gateways which are directly communicating with the interlocking. So you don't need a data concentrator in between, because the protocol is only the main application is already a TCP protocol, but a specific protocol which has to be implemented at the CTC level, so that is taken care with the field gateways. So these are the different types of field gateway implementations that we define for a centralized control system and a TMS system. And then I request Ravindran to carry on the basic and advanced features of the TMS solutions.